Introduction to One-Dimensional Finite Difference Method. In this video, I am going to try to describe what the finite difference method is, what it is doing, and then show you two different ways that it can be implemented. The conventional finite difference method that you'll learn in all the textbooks and all the different numerical methods classes out there. And then I would like to show you what I think is an improved way to implement the finite difference method that I think greatly simplifies the formulation of the method, where you go from the differential equation to the matrix equation, simplifies your codes, and I think it's just awesome. And with practice, given an entirely new differential equation or system of differential equations, you can often have that solved within minutes. It's absolutely an incredible way to implement things. One drawback might be, as the problem size grows to something very, very large, the way this is implemented may not be the best at that point. But by the time you're tackling super large problems, you're rather advanced at this and you're ready to solve it by different means. So let's jump right into this. Introduction and problem setup. In a nutshell, the finite difference method is a way of obtaining a numerical solution to a differential equation or a system of differential equations. It's important to realize we're not going to come away with a symbolic solution here. Now, we may get the solution and recognize, oh, that's a Bessel function or a sine function, and then that may give us a clue to go back and figure out how to solve it analytically. But the finite difference method will just give us a series of numbers that we can plot, and that's the answer to the problem. So we'll start off somehow with our governing equation or system of governing equations. I'm just showing one here. So we have a differential equation, we have boundary values, we have a certain range we're interested in. Somehow we define the problem. This is where we apply the finite difference method. And we approximate the derivatives with finite differences. We have to make our function y discrete. We get a system of equations because we write that finite difference equation once for every point in this array. And we put that giant set of equations in matrix form. And really, the finite difference method is what takes us from our analytical differential equation to the matrix form. So finite difference method lives here. Once we have this matrix equation, we really can kind of forget about how we went into matrix form and just think of this y as our unknown. And if we solve that for y and plot it, we will get our answer. So this last step here, we can kind of forget that we solved this by finite differences. Maybe it was finite elements that brought us here. Maybe it was the method of moments or something else entirely. So finite difference method lives here, and then we can plot our answer. And in a nutshell, this is what we're trying to do. And notice, this is not a symbolic answer. Now, we may get a function that we recognize as something symbolic, but it is not a symbolic answer. We're getting a series of numbers that we plot, and that is our answer. So a key thing to remember in the finite difference method is that our functions are discrete. Well, really, we know that functions are smooth and continuous, but there's an infinite amount of information here, and we want to solve this numerically. So the way that the finite difference method does that is that it stores this function only at discrete points. And really, we don't know what the function value is between those points. We can make good guesses doing things like interpolations or whatever else, but the reality is we don't know, and we want to formulate our method so that we don't care. All we really need to know is the function value at these points after obtaining a solution. We can also tell at this point that the more closely spaced these points, the better off we're going to resolve that function. But of course, that's going to lead to more finite difference equations, slower simulation time, larger memory requirements. So there's a trade-off there. And very often we have to try to understand how quickly varying our solution might be. And there's ways we can make good guesses at that. But oftentimes we'll have to find the answer and then maybe go back and add more points and solve it again. The last concept before we move on is that we are storing our discrete functions as column vectors. So we will take our initial differential equation And now imagine factoring out the y. So we have all of our differential operators lumped into this parenthesis here, and we have our unknown function y and then a bunch of zeros over to the right. When that ends up in matrix form, it's really this group of operations that define this square matrix A. The zeros over here will just be a whole column vector of zeros, right? Because we're writing our finite difference equation once for every point in our array. And so this will have that many rows in it. Our unknown is also stored in a column vector. And so it will be a one-dimensional array of numbers such that when we plot it, we will see our answer. Now, we don't know this answer until the end, so when we're initially building this matrix equation, this is not known. We have to build it and then solve it for y. Conventional finite difference method. The first thing I'll step you through is really how the rest of the world implements the finite difference method. And so we start with our governing equation, our boundary values, the interval that we want to solve things in, and we want to proceed from here. So we have our differential equation, and our first step is to make this discrete. So, okay, now our function y will only exist at discrete values of x. That allows us then to use what we know about finite difference approximations to approximate our derivatives. So here we see a second order derivative of y with respect to x. We now know how we can write that. Y at the next value of x minus 2 times the value of y at x plus y at the previous value of x, all divided by the spacing delta x squared. We now know that that is a second order derivative, the finite difference approximation for a second order derivative. We can move over to the second point and write this as y of x minus y at the previous value of x divided by the spacing delta x. That's a first order derivative. And y, we don't need to do anything with that. That just is y of x. And of course, the 0 at the end, we also don't need to do anything with that. But here's an important part about writing finite difference equations. Every single term must exist at the same point in space. If this also had time in it, I would also say every term must exist at the same point in time and space. Here we just have x. So we need to figure out where these finite differences are defined. If we look at the first term, well, that's really calculating the second order derivative at x, right? Because this x is the center value of all of these numbers. And we recognize the form of this finite difference as calculating the second order derivative at the midpoint. Over here, interpreting this as a central finite difference, it will exist at the midpoint between x and x minus delta x. That means this term exists at x minus delta x over 2. And then the last term, well, of course, that exists at x, and the zeros we can just define to exist anywhere. Well, at this point, we see the problem. This second term here does not exist at the same point in space as every other terms. Now, sometimes you can get away with this, but many times this is going to lead to an unstable finite difference solution. And so we don't want this. We need to fix this. We need to somehow do a first order derivative so that it exists at x, so that the entire equation exists at the same point. Alternatively, we could fix all the other terms so they somehow exist at x minus delta x over 2. Of course, I think it's easier to fix one term than it is to fix everything else. So that's what we will do. Well, here's how we can fix that. Every term here is the same as on the previous slide, except this one. And so now what we'll do is we will take the value at the next value of x minus the value of y at the previous value of x. So now we're spanning 2 delta x's. And then, of course, we'll divide by 2 delta x because that's the space between them. That's what we need to do to approximate a first order derivative. Well, interpreting this as a central finite difference, it will exist at the midpoint between these two, which is at x. So every term here exists at a value of x. So that's the big rule. When we write a finite difference equation, every term must exist at the same point in time, and space, although we don't have time here to really demonstrate that. So we have a good, stable, finite difference equation. We are ready to proceed with this method. So I don't like finite difference equations in this form. I think it makes more intuitive sense when we first start thinking about finite difference equations. But in a computer code, we're working with arrays where you have your first element, second element, third element. And so writing things this way, it's not entirely clear to me, is this the first, third, seventh element? So I like writing my finite difference equations in terms of array indices. So that's what we're doing down here. And I'll also admit, I'm always a little bit torn on how I like to do this. For me, for short equations, I like to write the array indices as subscripts. Although I think by doing this, sometimes it's easy to lose track or lose sight of the fact that these are arrays. And so sometimes I will still write these in parentheses. However, it just makes the equation a little bit more larger and more difficult to work with. So this is my personal preferred notation, but it makes it so you can lose sight that these y's are actually arrays. So let's go with this so it's a nice compact notation. But stare at this, maybe pause the video so we can see that these two really are the same thing, but I now is an integer that goes 1, 2, 3, 4, 5, 6, 7, 8, all the way to the number of points on our grid. Now we want to rearrange the finite difference equation. So in its present form, our finite differences are quite apparent. However, we have to build a giant matrix, and it'll be a lot easier to do that if we rearrange this. So the first thing I'll do is just completely multiply this thing out. We're here. And then I'm going to collect the common y terms so that we only have one occurrence of y sub I minus 1, y sub I, and y sub I plus 1. And our constants have collected into these coefficients in parentheses. But once we set up our grid, we'll have numbers to put the delta x. So what's in parentheses, we can put numbers to, which is our next step. So for us, let's set up a grid and solve this on a grid with 21 points, which means we'll have 20 spaces. So if we want to calculate the grid spacing, we take the last point minus the first point. That's the total span of space that we're solving this over. So xb minus xa, and we divide it by n minus 1. So we have n points, but n minus 1 spaces within there. So 21 points or 20 spaces gives us a delta x of 0.5. Now we can go back to our finite difference equation that we rearranged, and we put in 0.5 everywhere we have a delta x. And then we do the math, and we end up with this deceptively simple equation. But now this equation is very specific to that grid that has a spacing of 0.5. If we change the spacing, clearly the numbers in this equation will have to change. But it's this equation that's going to enforce our original differential equation, and we will have to write that equation for every single point, every single one of our 21 points across space. So that's what we're doing here. We go ahead and we write this equation, which is our finite difference equation, although it does not look like finite differences anymore. And in fact, you know what? Maybe it was finite element that got us here. So we can kind of forget that this was a finite difference at this point. We just have an equation that enforces our differential equation at every point on the grid. We have 21 points, so I'm writing this equation 21 times. And maybe you want to pause the video, look at each of those equations, and see how it's doing that. But looking at these long enough, we're going to recognize there's two problems here. Our equation wants to access the point before I and also the point after. So if we're trying to write this equation, let's say at the first point, it wants the 0 point, which does not exist. And that's right here. We need a 5 times y naught to write our finite difference equation for that first point. Likewise, if we're at the last point, we need y sub 22, which also does not exist. They both exist outside of the grid. So we have a problem almost anytime we write our finite difference equation at the boundary points. And When this is solved, that's called our boundary conditions. Not to be confused with boundary conditions that we discuss in physics or differential equations, which is really what happens at the interface where two discontinuous functions meet, or I shouldn't say discontinuous, two different functions meet and we want to actually make them continuous. Now we're talking about we have this numerical problem at the edge of the grid and we have to somehow solve it. So it's happening at the boundaries of our grid and we need some kind of boundary condition to solve that. Well, for us, we have an easy solution. We actually know the boundary values. We know the value of y at the first point is 1. That was given to us in the very beginning. And the value of y at the last point was 5. So what we can do is just literally throw out the first and last equation and replace it with the first equation is just simply y1 equals 1. And the last equation is simply y21 equals 5. At this point, we can take this huge set of equations and put them into matrix form. Here's another place where you might want to pause the video and look at how each one of these equations got incorporated into the matrix equation. I'll just look at two. Let's take this first equation, y1. So remember, each column is referencing a different y. So the first column is referencing y1, the second column y2, y3, y4, and so on. So in this first row, we have all zeros except the one in the first position. So that's simply just multiplying y1 and everything else gets zeroed out and isn't accounted for. So on the left, we just have y1 equals 1. Let's go to the second equation. We have 5y1 minus 7y2 plus 3y3. Now if we go over, we have 5 multiplying y1. We have minus 7 multiplying y2 and a positive 3 multiplying y3. The rest is 0, so they're not even there. So we do have 5y1 minus 7y2 plus 3y3 equals 0. So our 21 equations have been put into a matrix form, and this is a 21 by 21 matrix. Now, rather than keep writing all of these numbers, which can get quite cumbersome, let's just write this big first matrix as A. And remember, A really has incorporated the rules from our differential equation. Our derivatives and things have lumped into A. Our unknown we're storing as a column vector. And over here on the right, all of our constants we're also storing in a column vector B. Sometimes this is called the excitation, because if this is all zeros, we can't solve the problem. We need some numbers over here that's somehow defining something about our problem so it can be solved. In our case, it's a boundary condition. In an electromagnetic simulation, that might be a source wave. In some other kind of simulation or calculation, it's something else. But we need it not all zeros. Okay, so here we are. Now we solve that matrix equation on the previous slide for y. So what you see is the inverse of this big matrix, multiplying that column vector B. And if we do the math, of course, we're not going to do this by hand. We're going to somehow enter this into MATLAB, and MATLAB does it for us, and it calculates a whole bunch of numbers, which hopefully is the solution to our function. And what we see is that our boundary condition at the first and last point is satisfied. But then we got to think, does that make sense? And so the last thing we'll do is plot our function, and that's what we're seeing. We're seeing a whole bunch of points, and of course it drops really sharply here. And at this point I'm looking and seeing, what, that forms some kind of continuous function. I can follow that. I might look over here and think, those points are getting a little bit sparse. I might want to go ahead and say 21 points, maybe try 41 points or 50 points or 100 points or something. And usually what I'll do is just keep cranking up the number of points until my answer doesn't change much anymore. That's called convergence. We saw that a little bit when we talked about numerical integration. Same thing's going to happen here. We'll check for convergence with our number of points on our grid. Improved finite difference method. Let's repeat everything we just did, but with a new method, and I hope this illustrates the simplicity that this buys us. We have the same starting point, the same governing equation, same boundary values. We're solving the same problem, just with a different way of implementing the finite difference method. Now what we'll do for formulation, rather than go through the whole ugly thing with finite differences, we're just going to go term by term and immediately write our differential equation in matrix form. We already know that our unknown function y of x is always going to be stored as a column vector. Likewise, the zeros on the right is a column vector. Those are the only two things ever in a differential equation that's stored as a column vector. Everything else is not a function. Everything else is something operating onto those functions, and they are stored in square matrices. So here we have a second order derivative operating on y. So we're going to have some kind of square matrix operating on y. Now we have, of course, minus a first order derivative operating on y. So we have a square matrix that is somehow a first order derivative operating on y. Then, of course, we just have y, we just have zeros. So this is easy. And with practice, mentally, you don't even really have to do this step. I can look at this original differential equation and just sort of see this in my head, but it's still okay to write that on paper. Now what we'll do is factor out the y. So we have our two derivatives, and when we factor out y from something that's only y, we need the identity matrix here. That's the only little trick. But basically, the differential equation is now lumped into these what's in parentheses here, and so our differential equation is operating on y. At this point, we're in standard form, and I call this standard form. So a times the unknowns equals zeros, and we need to think about that because remember, a matrix equation ending in zeros isn't really solvable. But here's a. And with practice, I can just look at the differential equation, just sort of mentally erase the y's and just imagine this in my head. And so what we'll have in our MATLAB code, there'll literally be a line of code where we're typing that in. And so the only thing we really need to discuss is how we build these derivative matrices. And what we'll do is we'll program a function into MATLAB where we tell it the size of the grid and the spacing. That's all the information it needs. And it will build these matrices for us. And you'll also see that building these matrices is very simple. So that's one line of MATLAB code. You'll say, we'll call it some kind of derivative matrix builder function, and we'll hand it the number of points and the size of the grid, and it spits back our derivative matrices. That's one line of code. Second line of code, I really feel like I'm literally typing in the differential equation. And this, in my mind, is your superpower, where you can literally just type in the differential equation. So if you have a new differential equation, it has the same derivative matrices. All you do is type in a different differential equation and you're solving something entirely new. This is very fast, very simple, and we're no longer even explicitly touching finite differences. Yes, it's happening behind the scenes, but we don't really have to worry too much about that anymore. All the tediousness of the finite difference method has gotten absorbed into that function that builds these derivative matrices for us. Really, really cool. So at this point, this is not solvable. We have all zeros over here, and while we need to incorporate our boundary values. So that requires us to do this in two steps, and it'll turn out doing this in MATLAB code is also very simple, like 2 lines of code. So we're going to zero out the first and the last row. So we're throwing out that finite difference equation. Then we insert ones in the diagonal positions. So we no longer really have a finite difference equation at the first and last point. We've thrown that out and just put a 1 in the diagonal position. And then the very last thing is over here in this B column vector is insert our boundary values. And it will turn out doing that in MATLAB is very fast and very simple. We are now at the exact same place we were when we applied the conventional finite difference method. This is the exact matrix, the exact B column vector, our exact unknown. And so the solution from this point forward becomes the exact same. So we'll now do a inverse of this matrix times our column vector, and that gives us our unknowns. And we get the same answer. And we plot it the same way. But in my mind, we got here a lot quicker. So now imagine I hand you a new differential equation. If you're applying this technique, all you're going to do is type in this new A and perhaps define new numbers for the boundary conditions. Done. You'll hit run again. That is super, super quick. Whereas if you're applying the conventional finite difference method, well, if you have a new differential equation, you'll have to start there, approximate with finite differences, make sure all the terms exist at the same point in space. Maybe you have to modify those, write it in array form, then rearrange to collect terms for constant y terms, then put in your value for delta x, so you get an equation all with numbers, then build your matrix, then go back, incorporate boundary values, and then finally solve it. It's hugely complicated. And so it's even more complicated just for that one simple differential equation. Imagine that differential equation is a more complicated one, or imagine you have a set of differential equations. This conventional approach is very, very difficult, in my opinion. It's very tedious. With this new and improved method I've shown you, all of that becomes very, very simple. A really neat approach. From the bottom of my heart, thank you very much for watching this video. I love hearing your stories about how these videos helped you. I also love answering your questions. So please tell me your stories and ask your questions in the comment section. I promise I will try to answer every single question that's asked. If you like this video, hit the like and subscribe button. I also recommend visiting the official course website that has links to the latest versions of the notes, the latest videos, and there's lots of other resources to help you learn, including implementations in MATLAB. I'll see you in the next video.